Hi everyone, welcome back to Data Science in Your Pocket. And today we are talking about what are foundational models. We are trying to touch the surface, what is required to build a foundational model, how they're different from LLMs, and different aspects of it. This is more of a technical video, so it's not displaying you any fancy tutorials, but it would be talking more about the machine learning concepts that goes into building a model like ChatGPT. So let's get started. First of all, we'll try to understand what is a foundational model and how it is different from an LLM. Do remember that an LLM is a type of foundational model, but all foundational models are not LLM. Any model trained on huge, diverse, general purpose data sets are called as foundational model. LLM is a type of foundational model trained on language, right? So these are built to understand broad patterns and generalize over task. Now the data set that we are talking about can be from anywhere. It can be chemistry, it can be doctors medical data set, it can be payments, etc. Now, what is the purpose of building a foundational model? They are reusable. Yes. So once you create a foundational model, you can now fine tune it, if you have heard of this term, to use it for different purposes. So basically, for example, you build a model like ChatGPT. Now you can fine tune this model to understand legal documents, use it for summarization and whatnot. For now, also, this model would be able to do all these things, but not at great accuracy, right? These models are general intelligence models. So basically, assume them to be a class 12th student that knows everything but is not specialized at anything. LLMs versus foundational model. What is the key distinction? As already mentioned, all LLMs are foundational models, but not all foundational models are LLMs. Foundational models specifically for language are called as large language models, while foundational models are trained on generality across any modality. Now, this modality can be anything. So, recently you might have heard of Google released Times FM. So, it was a time series foundational model. It can't understand language, but it can understand time series, any type of. Similarly, Stripe recently announced they have achieved 98% of fraud detection, I guess, on payments, building a foundational models for payments. So most probably they train their foundational model just on transaction data. So this is the difference. Examples, I think, as you must be understanding, GPT-4 Chat GPT is a language foundational model. Stable diffusion is an image foundational model. It can generate any type of image but can't generate text. Meta SAM, if you have heard of it, segment anything model, is a foundational model for image segmentation. Any sort of image segmentation it can do. Google's Times FM, as I was mentioning, foundational model for time series forecasting. So here you can see that the engine tokenizers. So when you talk about foundational model, when you are not talking about language, so when you're talking about LLMs, there are a lot of tokenization algorithms like byte pair encoding, word piece you might have heard of, sentence tokenizers are there. But once you move out of language, non-language models, this becomes a very important task, how to define the tokenizer, because tokenizer is basically defining the basic unit of that domain. Like for example, in case of text, we have algorithms like BPE and sentence piece, right? Now, how does a stable diffusion does the tokenization? It is taking patches of images. It is not using the same logic as text. In case of speech, it can be spectrograms, raw waveforms, etc. Time series, it can be trends, slopes, seasonality. Financial data set, it might be transactional patterns, even tokens like this is the amount set, this is one token, this was a date of transaction, that can be a token. In chemistry, it can be molecule graphs, mile strings, etc. So the role of tokenization, what is the basic unit of this data set that you want the model to learn, is very, very important to define. And this is a very tricky task. You might be thinking that's easy, but it is not at all easy. Now, training and large language model versus a foundational model. So talking about that, language models are natural language, while in case of foundational model, the data can be anything: sequences, audio, images, text. Tokenizer, as you mentioned, we have already have algorithms for language models like BP, WordPace, but in case of foundational model, the tokenization depends a lot on the task you are doing. So it would be custom logics that you might be using. I was reading Google's Times FM paper and they mentioned that they have been using a custom logic for that. So most of the time, it might be the case that you would be using a custom logic for tokenization, defining the basic token of your problem statement. What are the objective? Causal LM, MLM. Causal LM is basically uh, predicting the next token, and MLM is mass language modeling. So these are tasks for training. So let me take a step back. You must be knowing what is fine tuning. Now fine tuning is like training a pre-trained model and an already existing foundational model on a specific task. But how did we get to that pre-trained model? We need to train it on some more data set, some problem statement, right? So if you have heard of BERT, if you have read that paper, you might be remembering that it was trained on two pre-training tasks. One was mass language modeling. So what they did, they took the language and masked certain tokens within it. So like for example, the cat sat on the mat. So they might have masked cat. The mask sat on the mat. And now they're asking the model to predict it. And then other task was NSP, that is next sequence prediction. So they were inputting two sentences together and then asking what is the second sentence or the separator part. So these are the tasks defined for language model, but in case of foundational model, this can be completely different. They can't be the same. It might be the case that you might wish to have a hybrid problem as well. Output is text in case of LLMs, but in case of foundational model, the output can be anything. The output can be transactions. The output can be time series output. The output can be images. And challenges, as you can see, context length overfitting in case of language models, but in case of foundational models, deciding over the tokenizer, deciding what should the data set comprise of, deciding over what should be the pre-training task is very difficult. I think when you talk about foundational model, it's like moving in the dark. You have nothing to know, and you need to get all the screws one by one, deciding the data set, the modality, the tokenizer, the pre-training task, the loss functions. Everything has to be decided from scratch, and they can't be replicated from language models. Do remember that. Don't think that if you are able to train llama 8b using some method, the same method would run for times fm for Google. It won't, because they are two different types of data sets. Now talking about reality, compute cost, pre-training any language model. If I give you an idea how does pre-training, how heavy it is, pre-training GPT-3 costed about 355 GPU years. This is this heavy a task, right? So about 8 to 16 H100 GPUs, these are one of the best GPUs in the market, were running and required about 500k to 2 million GPUs for training. While in case of fine tuning is usually about 1000 tasks of pre-training. So this is comparatively way cheaper than pre-training, and hence you might be hearing that people are releasing fine-tuning script, but people usually don't train from scratch. This is because this is very expensive, very time consuming, and eventually if you do one mistake you are gone because you have wasted a lot of millions of rupees. But at times you would require to do pre-training when you are not dealing with language. So that's the case. That is why Google came up with times fm. You have image models coming into the picture. Talking about real world applications, you must be hearing that recently Stripe came up with a payments foundational model trained on billions of transactions. This was not paragraph, this was not text, this was transaction tabular data for fraud detection, spending habit analysis, merchant type classification, while Google came up with times fn model for stock market trends, sensor data analysis, weather forecasting, and we have image models also. Now, talking about an example, let's take something that hasn't been built yet. So, assume that I want to build a healthcare foundational model which understands prescriptions. Now, if you remember, in prescriptions, we have medicine names, the strength of the medicine, how many times it should be taken. So, it's a mix of text, as I've mentioned here. shorthands and codes. So this text is not entirely natural language also. So here deciding over what the tokenizer should be, what should be the pre-training task becomes a challenge. So I'm just trying to give you a heads up how it differs when you move out of language. While similarly in case of chemistry, assume that I want a model that understands chemistry very well. So we would be feeding it with just equations and these formulas. In that case, also defining the tokens is very difficult. Designing the pre-training task is difficult. The solutions is substructure aware tokens, chemical logic internalization, and whatnot. So it is heavily domain dependent on your foundational model building, and nothing is fixed in this case. So summarizing it all, foundational models are the reusable building blocks of modern AI. These are very difficult to build, and very few companies have even the resources to build it. You even if you wish to build it, you just can't. So they are reusable, they are generalizable, modular, and transformative. You can apply this foundational model once trained on any problem statement hovering in chemistry or hovering in medical domain. So these are this important, and hence companies have now started off with building out foundational models from scratch. And I hope we see some exciting models coming out soon. Thank you so much. I hope you like this video. It was more of a shallow introduction to foundational models, but soon I would be covering each aspect of this one by one, taking one general example. Thank you so much.